arrived, so please collect them from the photocopying shop by tomorrow, right? So that everybody gets a copy before the long weekend. Okay, are you ready? Can you take out your G-Field notes? Can I have some silence so that I can begin? Okay, just a quick recap. So last lecture we talked about the definition of gravitational potential. It is the work done by an external force to bring the work done by the external force per unit mass, right, in bringing a test mass from infinity to a point in the G field without any change in the Ke of the test mass. Right, and then we say that if the source mass is a sphere or a point mass, that means its gravitational field will be radial in nature, right? The field lines will point inward towards the center of the mass. And for that kind of situation, the potential equation can be written in this form, minus Gm over R. Big M here is the mass of the source mass. Okay, so the potential is always negative, and the value at a particular point in the field depends only on the distance r from the center of the source mass. It is independent of the value of the test mass because this work done is per unit mass. Okay? And then we see that potential is negative because work done by this external force is always negative. Right? The work done is negative. The initial energy of this unit mass at infinity is 0. Right? So the final potential that it has at that point in the field will be negative. When we talk about GPE, right, the relationship between GPE and the potential at a particular point, right, is that GPE equals to the mass of the test mass multiplied by the potential at that point in the gravitational field of the source mass, big M. Right? And so if you want to find the change in potential energy, the gravitational potential energy when we move the test mass, small m, from one point in the gravitational field to another point, then the change in GPE can be calculated by taking the mass of the test mass multiplied by the change in potential between the 2 points. Right, so for a radial field, right, you don't need to know the derivation, right? But then the GPE can be calculated using this formula, only for point masses or spherical masses, which normally we assume will be the case at A level in the problems that you encounter. Right? Take note there's also a negative sign here. Okay, then we finally ended off with the escape velocity. Right? To calculate the escape velocity, right, it is the minimum velocity the object must have to escape from the gravitational field to be able to go to infinity with minimum, what we call 0 Ke. Right? So to calculate escape velocity, we make use of conservation of energy. Total initial Ke and GPE equals to total final Ke and GPE. Right? And the GPE at infinity is 0. Okay, let's look at example 4. Right, so the graph shows you how potential vary with distance from a planet center. So based on this graph, you need to determine the potential at point x here. You are given the value, the potential at point y is minus 20 megajoules per kg, right? Take note of the unit, is megajoules per kg. And the distance is km, 10 to the power of 3 kilometers. Okay, how do you find potential at x? So in this case, we've got to assume that the planet is spherical in nature, right? So that its gravitational field is radial. Then we can use a formula, potential equals to minus Gm over R. Okay, so that's our assumption for this planet is spherical. How do we find the potential at point x? If it's spherical in nature, the potential at point x will be Gm minus Gm over Rx, the distance of point x from the center of the planet, which is 5 times 10 to the power of 3 kilometers. Okay? But we do not know the mass of the planet. It's not given. So how do we determine the mass of the planet? And that's why they've given you the potential at point y. Okay? So potential at point y, right, we can determine using this formula, minus Gm over Ry. Big M is the mass of the planet. Ry is the distance of point y from the center of the planet, which is 4,000 kilometers. Okay, and then the potential at this particular point is minus 20 times 10 to the power of 6. Right, so the value of the potential at point Y allows us to calculate the value Gm. And from there, you can actually determine the mass of the planet because the value of G is given to you, right? It's given to you in a data list, but it's good to remember the value of big G. But for now, I'll keep it as Gm because the question didn't really ask for the mass of the planet, right? So I will keep the value Gm as a constant. So once you have the value of Gm, right, big M is the mass of the planet, you should be able to calculate the potential at point X. We use back the same formula, right? Just that now the R would change to Rx, the distance of point X from the center of the planet. Right, and just a final check, your final value for potential must be negative. Gravitational potential is always negative. Unless you're at infinity, then the value becomes 0. Okay, if you're done with part A, look at part B. Can I move on to B? Okay, so here you're moving 100 kg test mass from point X to point Y. And what is the change in GPE? So potential, this graph is on potential. How is GPE related to potential? Right? GPE equals to the mass multiplied by the potential at that point. Right? And this mass here is the 100 kg mass. So we're finding not GPE, we're finding change in GPE. Right? So delta GPE equals to the mass times the change in potential when you move from X to Y. Okay? Change in potential is always final potential minus initial potential. Right? So it's potential at Y minus initial potential at X. And then you sub in the values you've calculated earlier. Be careful of the negative sign. It's a minus subtracting a negative number. So it's minus minus. Finish already? Okay, let's look at C. Find the G field strength at point X, right? So for a radial field, we can calculate the G value, right, the field strength, using Gm over R squared. Because I'm talking about the G field strength at point X, the R will be the distance at X, right, from the center of the planet, right? So this Gm would be this big M is the mass of the planet. So is this value you have calculated earlier? Just be careful of the units. and the values used in the graph, right? Megajoules, right? So remember, 10 to the power of 6. And this is 10 to the power of 3 kilometers, so 5 times 10 to the power of 6. All done? Okay. Okay, we talk about equipotential lines. Okay, what are equipotential lines? They're lines of constant potential, meaning that along an equipotential line, the potential at every single point along that line must be the same. Okay? And equipotential lines, they're always perpendicular to the gravitational field lines. Right, so here, the red concentric circles you see are the equipotential lines around Earth. Right? So let's look at the outermost circle. Along every point along this circle, right, the potential, the gravitational potential is the same. Right? It's called an equipotential line. And because Earth is a radial field, right, the field lines, they converge at the center of Earth. Right? So that's why the gravitational, the equipotential lines being perpendicular to the field lines, they will be concentric circles. Right? At every point along the circle, you can see, is perpendicular to the field line, which is radial. And you also notice that closer to the surface of Earth, the equipotential lines, right, the circles, they are spaced closer together. As you move further away from Earth, right, the equipotential lines are spaced further apart. So the spacing of the equipotential lines also give you an indication of the gravitational field strength. When the lines are spaced close together, the field is strong. Further away from Earth, the gravitational field becomes weaker, so the equipotential lines are spaced further apart from one another. Field lines also space further apart from one another. Okay, equipotential surface, similarly, right, they are a surface on which the potential is the same at all points. Okay, equipotential surfaces always perpendicular to gravitational field lines as well, just like equipotential lines. Right, so because the potential is the same across any point along the surface, on the surface, when you move from one point to another point on the surface, no work is done. Right? Assuming you move at constant speed, right? Then the change in potential energy is mass times the change in potential, which is zero, because it's an equipotential surface. So there is zero change in GPE, right? No work done. Right? The spacing between the surfaces will be closer where the field is stronger. Near the surface of the Earth, right, we say that the gravitational field is approximately constant, so the equipotential lines will be uniformly spaced. Which means that for every meter that you raise a 1 kg mass, right, this 1 kg mass will gain 9.81 joules of GPE. Okay? That's near surface of Earth. Right? If you are very much further away from Earth, right, where the G field strength is, the G field is much weaker, then the gain in GPE will be less than 9.81. Right. So yeah, the field lines or the equipotential surfaces, they become more spaced out as you move further away from the surface of Earth. Okay, now we're going to talk about gravitational potential gradient. So over here at the center, we have a source mass. Okay, let's say it's a planet of mass big M. Then I have a test mass here, right? Mass small m is located at a distance r subscript I from the center of the planet. Okay, so what I want to do is to move this small mass, right, to the outer circle, where it's at a distance r subscript f from the center of the source mass. Okay, I want to move it away at constant Ke. Okay, which means that the net force exerted on this small mass must be zero, so that it can move at constant speed. And that means that I must apply an external force away from the source mass, and the magnitude of this external force must be equal to the gravitational force which this source mass exerts on small m. Correct? So as I move, okay, let's say I am applying this external force. As I move away to r subscript f, let's say this is just a short distance away. As I move away, this external force, right, it is exerted in the same direction as the displacement of the small mass. So what can I say about the work done by this external force? Positive work done. So what happens to the energy of the small mass? Must increase, right? But we see that we're moving it at constant speed. So Ke cannot change. So where did the energy go to? Increases the GPE of the small mass. Okay? So the work done by this external force goes to increase the GPE of the small mass. Right, so work done by this external force equals gain in GPE. And I'm assuming that the distance I move is a small distance. So the gravitational force from this circle to the outer circle should be more or less the same, right? If it's just a small distance away. And that means the external force that I apply, I assume is a constant value. Now, if you're going to move it very far away, gravitational force will change, right, according to the equation gmm over r squared. Then your external force will also be changing as you move the mass out with constant speed. Right? So here it's important to remember that we keep the distance small so that we can assume this external force that I apply will be approximately constant in magnitude. Right? That helps us to simplify when we calculate the work done. Right? Because it's a constant force, I can say it's force times displacement. If this external force is not constant, then to find work done, you need to do integration, right? Which we will not do at this level. Right? So you take it to be a constant force because you are moving through a small distance. So force times the displacement, which is Rf minus Ri, equals to the change in gravitational potential energy. In this case, the change is a positive change. The mass gains GPE. So the subtraction, I can write it as a delta R, right? So external force times delta R equals to delta U, the change in GPE. Right, then I bring the delta R over to the right-hand side. So external force is delta U over delta R. If delta R is very, very small, then delta U over delta R becomes du dr, right, the differential. And what is external force? External force is equal in magnitude to the gravitational force but opposite in direction, right? So F external equals to minus Fg, the gravitational force. So I can substitute minus Fg into this equation, I will get this equation. Gravitational force equals to minus du dr. Okay, this is an important result you need to remember. Du dr is the rate of change in gravitational potential energy with distance away from the source mass. There is a negative sign here, right? Is that part of the magnitude? F is a vector, right? So for vector quantities, the negative sign is not part of the magnitude. It is an indication of the direction of the gravitational force. We'll come back to that later. Okay, but just remember, right, this result. From this result, I'm going to derive another set of equation. Fg is the gravitational force. It can be calculated by taking the mass, small m, times the gravitational field strength at that point. And gravitational potential energy is mass times gravitational potential at that point. Okay? So this equation that we've just looked at, I'm going to substitute gravitational force mg into the left-hand side. Right? And then this u, I'm going to substitute m phi. Okay? In this differential, the m is a constant, so I can bring it out. And then the common mass, you can cancel on both sides of the equation. So you end up with a similar equation, this time involving gravitational field strength and gravitational potential. Okay? Gravitational field strength is equal to the negative of the rate of change of gravitational potential with distance away from the source mass. Again, the negative sign, right, indicates the direction of small g. Gravitational field strength is a vector, so the negative sign indicates its direction. It's not part of the magnitude of g. So these are two important results that you need to know. Okay. So if they ask you, okay, how is gravitational field strength related to gravitational potential? Right, it's through the equation. The gravitational field strength at a particular point in the G field is equal to the negative of the rate of change of gravitational potential with distance right, from the source mass. Similarly, if they ask you how is gravitational force related to gravitational potential energy, right, you can actually explain. It's very similar, it's just that the G is replaced by F, potential replaced by potential energy. Okay, a few things to note, right? This term, d phi dr, is called gravitational potential gradient. And it is a vector quantity because G is a vector. The magnitude of the field strength at a particular point is equal to the magnitude of the potential gradient at that point. Okay, meaning that if I were to give you a graph of potential against distance, like what we've seen in example 4, then the gradient of the graph gives you the magnitude of the field strength G. Okay? And the negative sign, we say, is an indication of direction. So in this equation, this negative sign tells us that the G field acts in the direction of decreasing potential. Okay, so if you are talking about Earth, right, you know that the G field strength acts towards the center of Earth. Right? That means if you move away from far away towards Earth, surface of Earth, as you move in the direction of the G field, the potential must decrease, which is what you have experienced, right? GPE decreases as you move closer to the surface of Earth. Right? That's what the statement is trying to say, right? G field acts in the direction of decreasing potential. Okay, so far? Okay, this part here, it might get a bit confusing for some. So can you take out a piece of paper, a foolscap or blank sheet of paper, as I go along to explain how we sketch the various graphs that we're going to discuss here now. Okay, please write down the steps that you do, that we take to sketch those graphs. Because you need to know how to sketch them yourself. Right? If you look at your notes a few weeks later, you may not remember how we get those graphs. Okay, first graph we're going to talk about, right, is a graph of gravitational field strength against distance when there are two masses present. Big M, small m, spherical masses. Big M is going to generate a gravitational field, right, around it. Same for small m, right? So if I have a test mass located in between the two masses, what is the resultant field strength? Field strength is a vector quantity, right? So if I have a test mass here, it will experience a gravitational field strength due to big M towards big M. It will also experience a gravitational field strength towards small m. So I must find the resultant field strength, okay, before we can sketch. Okay, first we draw the axis. I'm plotting G against R. Now when I draw R with the arrow pointing in this direction, it means that you're taking right to be the positive direction. And you will have to follow this convention. Right? You cannot suddenly choose left to be positive. Okay, always remember when you sketch such graphs, right, you take right to be positive. G field strength is a vector, so it's important you define your positive direction. So now I'm going to assume I have a test mass. Because I want to sketch G field strength, okay, so I assume that this test mass, its value is 1 kg, right, unit test mass. So this test mass, right, is going to experience a gravitational force that big M will exert on it. Which direction is that force? Towards big M, right? So the gravitational field strength, I call it G subscript big M. It is towards left. So what can we say about the sign of this G? Would it be a positive G or a negative G? Negative, right? Because we say we have taken right to be positive. So the G field strength due to big M, right, at this point will be negative. What about the magnitude? The magnitude is calculated using this formula, right? Gm over r squared. In this case, this is big M. Because Now only looking at the G field strength due to big M only. Okay, I ignore the presence of small m for now. So the magnitude, as you can see, the magnitude of small g is inversely proportional to the distance away from big M. Right? So the graph will look like that. It's negative because the direction of small g at this point, or any point in between the two masses, is always negative, right? It's always exerted towards the left side. At the surface of big M, the magnitude will be the biggest because the denominator r is the smallest. So it's the most negative. Magnitude is the largest. As you move away from big M, the magnitude will get smaller according to the inverse square relation. Okay, so this will be an asymptote. But take note, on the surface of the planet, the axis is drawn, right? The vertical axis is drawn at the surface, so we don't actually go into the center of the planet. We're interested up to the surface of the planet. So at the surface, it is not an asymptote. It is a finite value. The gravitational field strength on the surface of big M is a finite value. Okay? So we have the field strength due to big M. Now we're going to sketch the gravitational field strength, right, due to small m. So at this point in the field, right, if I have a unit mass placed here, that unit mass will experience a gravitational force exerted by small m in the direction towards the right. So what is the sign that we're going to assign? Is it positive small g or negative g? Positive, right? Because we take right to be positive direction. What about the magnitude of this g subscript small m? Again, it will follow this equation, and then now the m here is small m, right? Because the source mass now is this small m. We are looking at the gravitational field of the small m. So again, the gravitational field strength is inversely proportional to the square of the distance. So when I'm very close to small m, right, if this point here is shifted to somewhere very close to small m, the magnitude of the field strength will be huge, will be large. Further away, it gets smaller. Right, so the graph will look like this. Okay, again, take note, this dotted line represents the point at the surface of small m. The value of g is finite, right? It is not an asymptote. Because r is a finite value, it's not zero. Okay, if small m, the mass of small m is much smaller than big M, obviously, this value here, the magnitude must be smaller than the magnitude at the surface of big M. Right? Because the mass here, the numerator is smaller. So you would expect that the graph will start at a smaller value of g for the green graph. Okay, so you need to sketch the individual graphs due to the individual masses, big M, small m, and now you find the resultant. You just add up the two graphs. Okay, so I'm going to add the blue graph to the green graph. Right, at the surface of M is a very negative blue and a slightly positive green. So a negative plus a slightly positive value, you get a slightly less negative value. Over at the other side, right on the right-hand side, is a slightly negative blue value plus a positive green value, you get a slightly less positive value. Right, so if you join up the two graphs, this is the resultant. Okay, so the resultant, the variation of the G field strength in the region between the two masses, right, is illustrated by the red graph. You need to know how to sketch it. Right, so the question might just ask you to sketch. So what you do is to sketch the two dotted graphs, the individual field strength, and then find the resultant. Okay, and then the resultant, you can see, right, the magnitude of the resultant G field strength at the surface of big M is greater than that of the small m. Right, that's what I've said earlier, because the small m has a much smaller mass. So the G field strength, the resultant G field strength at the surface of small m will be smaller in magnitude than that at the surface of the big M. Okay, so when sketching graph of G versus R, you you need to bear in mind that direction has to be taken into consideration in deciding whether the graph will be a positive graph or a negative graph. And you always take the right side, pointing to the right, to be positive. Okay. Next question. Right, this position where the net gravitational field strength is 0, right, where it cuts the r-axis, will it be the midpoint between the two masses? Or will it be closer to big M or closer to small m? When you sketch, you must show where it cuts the r-axis. Right? Will it cut at the midpoint or closer to one of the masses? Where it cuts is where the net G is 0. Right? That means the resultant force at that position is 0. Force is given by gmm over r square, right? Big M having a bigger mass, right? If you're talking about midpoint, a point as midpoint between the two masses, at that midpoint, the gravitational force exerted on the unit mass by big M must be bigger than that exerted by the small m. Correct or not? Because gmm over r square, r is the same, right? You're at the midpoint. But big M has bigger mass. Right? So if it's at the midpoint, the gravitational field strength exerted by big M on the unit mass will be bigger than the force exerted by small m. So there will be a net force at the midpoint. The G cannot be 0 at the midpoint. For the G to be 0, right, it must occur closer to the smaller mass. Right? That's why it cuts the r-axis at a point that's closer to small m. It cannot be cutting at the midpoint. So when you draw this sketch, you have to bear that in mind. Okay, next graph we're going to draw potential against distance. Okay, so same thing of the two masses, big M and small m. I draw the vertical axis starting from the surface of each mass. Okay, how do I sketch potential? Right, let's look at the equation. Potential has no direction, it's a scalar quantity. So potential due to a spherical mass or point mass is minus gm over r. This minus sign is not an indication of the direction. It is part of the magnitude, which means that potential graph will always be negative. Okay? So we assume that we ignore the presence of the gravitational field set up by small m. Let's focus on the gravitational potential due to big M first. Okay? The graph will look like this. Right? Negative because gravitational potential is always negative. Right? And then the value of the gravitational potential on the surface of M will be minus G big M over R will be the radius of the sphere big M. Right? So again, it's a finite value on the surface of M, and it's not an asymptote. Then we draw the potential graph for small m. Right? Also negative, but it will start at a less negative value because small m, right? This mass is smaller. Right? So the potential will be less negative. Less negative actually means a bigger potential, right? Because the negative sign is part of the magnitude. And as you move further away from small m, right, the potential becomes even less negative. So you draw the individual graphs due to big M and small m, and then you find the resultant potential by adding the two graphs. Okay, so let's look at the left-hand side. At the surface of big M, it's a negative value plus a smaller negative value. So you get an even more negative value. On the other side, same thing, a negative plus a negative, you get even more negative. Right? So the resultant graph looks like this. There is a maximum point, right, where the two dotted graphs intersect. Okay, so over here, on the left-hand side, right, the value where it cuts the vertical axis, it will be more negative than that on the dotted axis, right? Because big M has a larger mass, so the potential at that point on the surface of big M will be more negative. Okay, a question. There is a maximum point, right? You compare this graph, potential distance graph, with the graph we drew earlier. G versus distance. Gravitational field strength versus distance graph. Right? This maximum point, which point does it correspond to on the GR graph? You understand? Potential, right? Where there is a maximum potential, which point does it correspond to on your G versus R graph? So you got to think of the relationship between potential and G. Gravitational potential and gravitational field strength, what is the relationship between these two quantities? Okay, at this maximum point, the gradient is 0, right? Gradient of this graph is d phi dr. Okay, so do you remember how is G related to d phi dr? We talked about it earlier in the lecture. G is minus d phi dr, right? The gradient, the negative of the gradient of this graph is equal to the value of the gravitational field strength. So at this maximum point, the gradient is 0. So G must be 0 at this position of R. Okay? So if you were to sketch this graph directly below the G versus R graph, the maximum point must occur at the same R as where your first graph cuts the R-axis, where G equals to 0. That is where the potential is the maximum. So if you sketch two graphs, you must make sure that your graphs is such that the maximum point corresponds to where G equals to 0, right? It must be proportional. Can I move to the next slide? Okay, so here is where we bring in circular motion. Okay? We talk about a body that's orbiting another body. So it's moving in circular motion, right? And what causes it to move in a circular motion? So here we have Earth, and then we have a satellite that's orbiting around Earth like this, okay? So for the satellite to orbit around Earth, to perform circular motion, there must be a force exerted on the satellite to provide the required centripetal force, right? Firstly, if the satellite is going around Earth, what is the direction of the centripetal force which the satellite must experience? Must be towards the center of Earth, right? Towards the center of the circle. Then the next question is, who provides this centripetal force? What is going to act on this satellite to provide that centripetal force you need to keep it in circular motion? Okay, so let's look at the satellite. What are the forces acting on the satellite? There's Earth, right? So Earth will exert a gravitational force on the satellite, which is the weight of the satellite, mg. Are there any other forces? No, right? There's only one force, the gravitational force. So it's quite clear now that this gravitational force is the one that is providing the centripetal force that the satellite needs to move in a circle. Okay? So we say the gravitational force exerted by Earth on the satellite provides the required centripetal force for this satellite to orbit around Earth, right? To move in a circular motion around Earth. Okay. So now we are to circular motion, solving circular motion questions, right? We always start off with summation of forces in the radial direction equals to mass times the centripetal acceleration, right? Newton's second law applied in the context of circular motion. So we're looking at only radial forces, and we must sum up all these forces, taking the direction towards the center of the circle as positive. In this case, simple, there's only one force, right? So mg equals to mac. Okay, I skipped one step. The gravitational force is mg. And mg, we have learned in gravitation, is gmm over r squared. AC, centripetal acceleration, there are three forms you can take. You can either choose v squared over r omega squared, or v omega. Right, so in this case, I'm interested to find the speed of the orbiting body. So I will choose mv squared over r. I will not choose omega. Right, I want the speed, not the angular velocity. Okay, so this G big M subscript E is the mass of the source mass, which is Earth, and the small m is the mass that's in circular motion, in this case, the satellite. And r is the distance, is the radius of the circle, right, which also happens to be the distance between Earth, center of Earth, and the satellite. Right, so the 2r you can cancel. Right, you end up with the expression for the speed of the satellite, right? Square root of g, mass of Earth, divided by distance between Earth and the satellite. Okay, what if you're not given the mass of Earth, but you need to find the speed of the satellite at a certain radius of orbit? What we can do, right, is to use this relationship. Gravitational field strength is g times mass of Earth over r squared. This g, right, it corresponds to the value at a distance r from the center of Earth, meaning that this g will not be 9.81 because your satellite is not on the surface of Earth, right? It is further away at a distance small r. Right, so this g will be much smaller than 9.81. Right, from there we know that the g, big G, gravitational constant, times the mass of Earth equals to gr squared. Right, g corresponding to the value of the field strength at position r. Right, so just now we saw this equation, we derived it. If you're not given the value of the mass of Earth, but you know the gravitational field strength at this position, right? You can substitute it into the equation, and then you get this. So depending on what you're given, if you know the mass of the Earth, of the source mass, you use this equation. If you're not given the mass, but you know the gravitational field strength at that position of the satellite, you use this form. Okay, now you try example 5. Right, the satellite's mass, small m, it moves in a circular orbit about the Earth, moving in a constant speed, meaning it's a uniform circular motion, and it is at a height 1,000 kilometers above the surface of Earth. Right, first calculate the orbital speed, small v. You're given the radius of Earth, and you know the mass of Earth. Right, so how do you calculate v? Circular motion, you always begin with the same step, right? The equation, Newton's second law. Okay, it's moving in circular motion, this satellite. What is the force that provides the required centripetal force? The gravitational force, right, exerted by Earth on the satellite. So you must write down this statement first. This one, take note, important. You have to write this down first. It's worth 1 mark. Before you write down the equation, summation Fr equals to mac, you have to first identify what is the force that provides the required centripetal force. Okay, this is necessary every time you solve circular motion questions. Before you use the equation, make sure you write down this statement. Identify the force that's providing the centripetal force. Right, then you follow up with Newton's second law. Summation of forces in the radial direction equals to mass times the centripetal acceleration. Right, if you don't want to write mac, you can straight away write mv squared over r. Here we want the speed, right? So I use mv squared over r. I know the radius of orbit. I will not use mr omega squared because I'm not interested in the angular velocity. Okay, then I'm ready to sub in values. Okay, what are the forces that can provide, that act in the radial direction? There's only one. That's the gravitational force. So I sub in the equation for gravitational force, gmm over r squared, mass of Earth, mass of the satellite. Over the other side, mv squared over r. This m here is the mass that's undergoing circular motion. So it's a small m, mass of the satellite. Okay, right-hand side, that's m here, is the mass that's undergoing circular motion. If I look at the equation on the left-hand side, when I use this equation, gmm over r squared, what is the meaning of this small r? What distance is this small r? Gmm over r squared, the r is the distance between the two masses, center to center. Okay? Over on the right-hand side, mv squared over r, circular motion. What is the meaning of the r? It's the radius of the circular motion. Okay? This r and this r, will they always be the same? In this case, yes. The distance between Earth and satellite happens to be also equal to the radius of orbit, right? But you'll see in your tutorial questions that it may not always be so. Okay, so you be careful what value you substitute on the left-hand side and the right-hand side for the small r. It may not be the same r. But in this case, it is the same. That's why I use the same letter r. Right, so you get an expression for the speed of the satellite. And then be very careful. This small r is the distance, is the radius of orbit, which is also the distance between Earth and the satellite. Right, so that is given by the radius of Earth plus the height of the satellite above the surface of Earth. Right, the question didn't give you the radius of orbit directly. They gave you the radius of Earth and the height of the satellite above the surface of Earth. And then just take note of the unit. It's 1,000 kilometers, so you multiply by 10 to the power of 3, convert everything to SI. Okay, once you have the speed, right, can you calculate the period? Can I move to the next slide, the last one, last slide? Now, how is period related to speed? Circular motion, we know that v equals to r omega. You know the radius of orbit, right? You know the speed, so I can find the angular velocity omega. Okay? So, omega, how is it related to period? Omega equals to 2 pi over t. Okay, so I sub in 2 pi over t. So from there you can calculate the period. Okay, next lecture will be on next Monday, right? That's our last lecture for this semester. Last lecture, you know, is always the most important lecture, right? It's the last lecture before your block test. So I'll see you next Monday. We'll finish up this topic.